And I will set myself as presenting. Do we want to start with us talking back and forth a little bit?
That's not a bad idea.
Okay, let me actually.
And let me.
Do that.
Which one did we say we were keeping
in? Zoom, actually. So let me do that on mine. Okay. Okay, so right now we are just talking back and forth.
Hang on, hold on. Okay, that's fine. I have the live stream up and it's mute.
Okay.
Enter picture in picture. So now I can see that and have some idea what's going on there.
Okay, cool. All right, I'm going to grab the link and post it. Well, I'll put it on Twitter, but no, I won't tweet it yet.
Tweet all the things also. Oh. I'll just retweet whatever you tweet.
All right, cool.
There's so much weirdness here now because I've got. I will just drop this in Slack so you see what it looks like because it's this when I have it all going. So many of both of us.
Okay, I'm going to tweet this in like 2 minutes.
Awesome.
So we'll just do a little intro of who we are. We'll wait a little bit. We'll wait about 10 minutes for everybody to kind of join, and then we'll say, okay, this is who we are. That's what we're trying to do.
I am going to actually go ahead and pull down your latest and have it up on my machine.
Okay.
So that we can move quickly toward that and then.
Good. And I did throw a copy of the practice branch main into a separate window for myself to like look at. And so if you refer to a function or something, I can go find it over there and look at it as well.
I'm going to kill most other things.
We have one viewer.
Who's viewing? Is it Ryan?
2 viewers. Oh, did we?
Oh, what do we have? Maybe it's you and me. It's probably you and me viewing it ourselves.
Oh, okay.
So confused.
Okay,
I don't know. So I have almost everything in place.
I really hope that Hangouts doesn't keep crapping out.
Yeah.
For you. Now, when Hangouts dies, how do you tell? I just stopped talking or what?
Basically, well, no, because I can still hear you on Zoom. Basically, I can tell that you can't hear me.
Oh, okay. How can you hear me on Zoom? I'm muted.
Interesting point.
Okay.
No idea. Maybe you did just go silent. Maybe that's what it was.
Okay.
But I'm going to make the Hangouts view be visible on the same thing as well, so that I can have a way of telling. I'm going to make that a small window.
Okay.
This setup is quite ridiculous, and the more so all the time. And things I hate about Zoom include that it constantly steals focus.
This is true. Yep.
Zoom is probably the worst app in terms of this experience, but it's also the most reliable actual video.
Yes.
What are you going to do, right?
Right. So many trade-offs. Okay.
That one doesn't seem like a necessary trade-off to me.
We're going to go pretty quickly through the parts that we've already done.
Yeah.
And yeah, if you can just kind of be, I don't remember exactly because we didn't during our practice session, we didn't exactly code in the order that we're going to do it now. So this will be interesting, but
walk through our basics and then
yeah, and let's try to have something compile at as many points as we can throughout, so that we're not waiting till the end for the grand reveal.
Concur. Something that can say, "Hey, look, you can do the things," is
right.
very helpful for people.
Yeah.
Okay, so you tweeted you. It looks like
I did.
Going to say something ridiculous. Here we go, elming all the elms.
Okay. I'm going to post this in a few other Slack channels I'm in.
Here we go, elming all the A stars. Because that makes so much sense. But good enough. And here I get to bust out the awesome podcasting mic too. Yay.
Cool.
Oh yes, and I should also tweet the last tweet since I actually published that. End of your episode. Copy that one. Copy that one.
Okay.
Done this before, so it should be a fun adventure.
Yes. All right. Let's see. Oh, Facebook. Maybe I can get my mom to watch.
I like that idea. I don't think anyone on my Facebook would ever care at all. Should we introduce Elm a little bit for anyone who hasn't elmed?
Yeah, good idea. Do you want to do that?
Yeah, I'd be happy to.
Okay, sweet.
I'll give it my best 1 minute pitch.
Okay.
YouTube chat? What is this YouTube chat? Oh, chatting chatters in chat? This is
We have chatters?
We do have chatters. Yeah.
Where do I see these chatters?
What do you mean create channel? I don't want to create a channel. I just want to chat back with the channel that already is chatting. So much chattery.
Leon, Ryan, Andrew. Nice to see you guys. All right. Okay.
Just pop out the chat so I can just have one more window going.
Yeah, it's getting kind of crazy here.
Enter picture.
Mm-hmm.
There we go. So now I have the Hangouts view and the chat view and the picture-in-picture view.
Can you ask them if they can hear us okay and if the volume is all right?
I'll hear you asking the question shortly.
If my audio works.
If your audio works. Huzzah. This is
Nice.
to everyone who's actually paid any attention to me's surprise, not coffee. This is hot chocolate.
It is kind of a hot chocolate kind of day, isn't it?
It really is. It was blustery.
It's actually pretty nice here today.
Yeah, it's 60 here, but it's blustery.
Okay.
I have closed everything else.
Okay.
Reasonably be closed.
Ben says we can hear. Good. Todd. Yeah. Tyler.
I think everybody can hear us, so.
Right on. 2 minutes.
Stay on target. There's a timely reference, right?
Right. Got a bad feeling about this.
I've got a bad feeling about shut up.
Okay. So once we do the intros, then I'll go ahead and share my screen and we can go from there.
Watching the lag is so weird. There's so much lag.
I know. You can actually, I think there's, this might be on Twitch, but I think that there's a setting for reducing lag, but then it causes problems with older computers and stuff. So as long as you know that you're excluding part of your audience, then you can enable that.
We're totally about excluding everyone, right?
So somehow they're able to do almost no lag with this broadcast here between us. But then I suppose because it's, you know, they understand it's only going to be a very limited number of people on it versus broadcasting to potentially thousands.
Thousands, yeah. So now I have it so that it's close to live. Apparently I was behind before. Now it's still not on target, but
okay, but not as bad.
Ben Collins, that's a pretty weird claim.
Permanently? That'd be nice.
Chris Krycho on 2x speed would be something else.
Yeah, yes, this is true.
All right, it's 4 my time and 1 your time because we're on the opposite sides of the country.
That's right. Awesome. Okay, welcome everybody. Thanks for joining us today. My name is Jamon Holmgren. I'm one of the founders and COO of Infinite Red. We're based, we're a distributed remote company. But I am actually based near Portland, Oregon. And with me,
I'm Chris Krycho. I'm currently a software engineer at Olo. We are a startup, sort of, but we're like 10, 11 years old now. We do restaurant ordering software. So if you order from lots of restaurants online, it goes through us. I write our front-end web apps in JavaScript, which means I have lots of reason to be interested in and excited about Elm, which is what we're actually going to be doing this in today. So on that note, I'm going to tell you a little bit about what Elm is on the assumption that some of you might not know, or you might only have heard of it. Elm is a language that compiles to JavaScript. It is part of a family of languages that have been coming out doing that in the last few years. First notable instance was CoffeeScript, but it's become fairly common now. Elm is also in a family of languages descended from ML. So if you haven't seen one of these before, it might look a little weird. It looks a little Haskell-y to some of you who might have seen that. It is a quote unquote pure functional language, which means you can't mutate anything. And everything is done by passing data around and basically piping it through a series of functions to get your transformations. And there are no things like loops. So you're going to see lots of fun times with recursion and some fun types, because Elm gives you nice type system. But in short, it's an interesting exercise to implement almost anything that you've only implemented in a traditional imperative language like C or JavaScript in something like Elm or PureScript or Haskell or any of these. But we're going to be doing that today. One of the first things I did when I graduated college, my job was implement a variation on this algorithm in C. I've never implemented it in any pure functional language, so this should be fun.
And I've always loved working with this particular algorithm, which is called the A-star pathfinding algorithm. And I last time I did it was probably 8 years ago. So yeah, I've had to really kind of relearn it, and it certainly was not in a functional language. I've been playing with Elm, really just kind of exploring the technology. My roots are software engineering. I don't do much anymore in my role at Infinite Red, but I still love it. So this is a great way for me to kind of explore that again. In order to fast forward this, we've done a little bit of work beforehand. And what we're going to do is I'll take you through the code right now. Let me share my screen and hope that Hangouts doesn't crash. Okay, hopefully everybody can see this. Now, what you're going to want to do is turn your quality settings on YouTube all the way up. So click the little gear icon down at the bottom and turn the quality settings all the way up so that you can actually read what we're looking at here. Okay, this is an Elm program. We're going to be doing all of our work in main.elm, which is essentially the entry point for our application. Over on the left here, I'll zoom in a bit. We have the Elm reactor running, which essentially just compiles the code and runs it kind of in real time. So we have a module main, which is our primary module. We're defining some functions. So on the left-hand side here, if you see like a name with a colon, then that is a function definition. This is a type declaration. This is our main program. I'm not going to go into that too much. You can look on Elm, the Elm Lang website to learn more about that. We have a couple of type declarations here, message, which are essentially events. We have a time tick, which happens every second, which will move our little dot around. And then we have a click event for setting a target, a new target, like you click on it. We also have two types of terrain. We have a wall, which you cannot go through. We have ground, which also includes inside of the ground, GR. It also includes a cost, which is a float. Then we have a type alias, which is an arena, which is a two-dimensional list. That's why there are two lists written here of terrain blocks. We have a character, has an X and a Y, a target X and a target Y. We have our overall model. If you're familiar with maybe React, this would be your state, so to speak. And that consists of one arena and one character. We have an init function which generates the initial model when we first come in there, which is init arena, init character. Ignore the command none. We're not going to be going into that in this particular session. The arena, the reason I called it GR is so that it lines up well with ground. If I change, for example, one of these to wall, then I can manipulate our map. Sorry, 1 second here. My kids are outside here, and I told them not to bother me, but we'll see how long that lasts. We're initting a character just with X, Y, and target X, target Y. This is our main update function. We'll be spending a lot of time in there, making sure that every tick or every event results in some sort of a change to our model, basically setting the state. We have a subscription. Every 1,000 milliseconds, we trigger the advance. And then our main view. This is like the render function in React. And we're creating a div. We have styles, which I'm not going to go through. We have an arena view, and we have a character view, just two views that get generated. And I'm not going to talk about this too much. You can look at, we do have.
Make it pretty.
What was that?
I said it's just there to make it pretty.
That's right, and you'll be able to see all of this. I already made it open source actually, so you can go look on my GitHub, Jamon Holmgren, to see what this is. I think it's under path. Let's see here, a couple of utility functions at the bottom, and let me show you what this does. So if I refresh here, you can see that we have a little dot disk, and it's going right through a wall and going to the target. But if I click anywhere else, it just goes directly toward it. This is the most naive pathfinding you can find. It's just purely what's the shortest distance irrespective of the terrain. So we need to make this much, much better. Okay, so let's get started. Chris is going to be kind of helping me drive, and we may hit some points where we don't know what we're doing, and we're going to have to figure it out. But
that's the fun.
Yes, we will do our best to keep things interesting, at least along the way here. So the first thing that we're going to really need to do is within the character, we need to store like a path. And you know what, Chris, I'm not sure if, yeah, my other branch actually had the path following stuff. So, well, I'll go ahead and code that in. So currently we're not following a path, we're just heading in the direction of the target. So we want it to follow a path. So I'm just gonna define a new, actually let's call it target path. There's a new property on this record, the character record. And this is a path type. So the path itself is a type alias, which essentially just expands. Anytime you type in path, it'll just expand to whatever you put here.
Right. So Elm has what's called a structural type system. So these things are made up of whatever the structure of them is. They're not named. They're not the same kind of thing as you would see in Java or C#, where it's a nominal type system and the name of the thing is the primary importance. The thing that's most important about this little record is that it's a list of things that have X and Y in them, just like that.
Yep. So I'm saying, yeah, it's a list of these things. And you'll see here that I got an error. It's telling me that init character does not properly match the type declaration. And that's because I didn't say target path equals, and then in our case, we're going to say an empty list. So now the compiler is satisfied.
Happy.
Yay. I'm going to run down to the update function here, and in the advance, I'm going to do something a little different. So what we're trying to make this follow a path, and we're going to just like hard code it first to show you how this works.
Show you that it does work.
Yes, exactly. So I need a new character, and what I'm going to do is just delete this. Since it's immutable, we have to create a new model and basically copy over everything and then update the properties that have changed. So this model will receive a new character, and we're just going to call that char. What we need to do is look at the current character, which we're destructuring from the model up here. And we have to look at the target path, that thing that I just made. This is how you write a case statement in Elm, is case of. And if it's empty, then we really don't want to change anything. Just stay where you are. Just, you know,
where we are.
We don't have a path.
Can you bump up the font size slightly?
Oh yeah, sorry about that. Whoa, is that okay?
And there's a request from the Slack channel, possibly also to maximize the editor.
Oh, yes, I can make it much bigger. Whoops. Sorry. Okay. Cool. All right. So what we're going to do is take the this is essentially this is destructuring the head of the list from the rest of the list. So just basically taking the first element of the list and assigning it to step, and then the rest of the list will be, we'll call it remaining path. And again, if we, whoops, no, sorry. All right, we have to do the arrow, sorry. That's the proper. Now we need to create a character that has, you know, the right X and Y coordinates. So we're going to take the current character, and we're going to update X, which will be, currently it's just basically going to be what it already was down here. So I'm just going to grab all of this and just drop this in here. And then instead of the target X, what we want is the step.x. So basically the next step in the path, remember the path is consisting of just a list of X and Y, right?
Mm-hmm.
So we're going to take the next X and the next Y, and we're going to head toward it. This code already works because we were already heading toward the target X and Y. So this should work as expected there. And then we get rid of all of this here. And let's save, I'm missing something here.
You missed a let. Should be let char equals that.
Oh, yes. Sorry. In Elm. Yes, go ahead.
I was going to say the let in gives you a binding for an expression. So when you're putting together something like this where you have these intermediate bindings, you need a let to bind them for the in expression. Elm is an expression-oriented language, so everything in it is actually just composed out of sub-expressions. And when you need intermediate values to plug into your later sub-expressions, this is how you do it, with a let binding.
And I screwed something up here.
Oh no!
So I think I deleted something I needed here. Sorry. So char, in this case, will be basically, let's see here. Actually, oops, I'm in the wrong spot again. In this case, we're going to say character equals, and then we're going to say character
with the updated X and Y,
target
right?
X equals.
Ah, yes.
Yes, and we need to change this to X and Y. Target X equals X, target Y equals Y. And we don't have a new target path yet, but that will come later. So where did I set the target? I'll go find that. It's down here. We need to reverse these to call row. Okay, so you can see here the on click just triggers off this set target with the column and the row, which we already know because we're rendering it there. And that's an int, basically. There's two integers, so we're just setting the target X and the target Y to those new integers. It looks like it went ahead and compiled, which means that it should work. So if I click here, it does set the target, which is good.
The target correctly. Yep.
And now let's test this this path out just manually. Let's go ahead and put a couple of path nodes here. So let's do
There's also a request from the chat that if you can make your audio louder, that would be a win.
Ooh, I don't know if I can. What do I have as far as controls?
Sound, maybe. There may also be some we're streaming through Hangouts, so settings there. Don't.
Okay. Okay, I'm cranking this way up. I don't know if it's any better. So testing 1, 2, 3. Oh, and by the way, whoops, sorry about that. Try this again. Screen 1, share, present to everyone. Okay. Should be much louder now. I don't know if it is, but
it is at least clippier. So.
So let's do this target path just to see how it goes. So we'll do 2 y equals 2. So it'll move to the right one, and then we'll do another one where it moves kind of down and to the right. So we'll say x equals 3 and y equals 3. So that's a new target path. We have no issues. So let's refresh, and it moves to the right, and then it stops. Did I do something wrong?
Looks like our update function isn't all the way done yet.
Okay, let's move back to our update function.
What are we missing here?
We're missing something. Oh, I need to update our remaining path. I forgot about that.
Yes.
So target path, because it didn't pop. Yeah, it didn't pop the rest of it off of there. So
right.
Remaining.
So it still thinks the next step is just to go to where it was.
Oops. It doesn't like that. Oh, that's because I need to move that into char.
Right.
Everybody on the stream saw that before I did. Okay.
But I didn't, so it's all good. We can all feel smarter than both of us.
Exactly. It moves to the right. Hey, it moved down to the right. Awesome.
Yep.
So
and
it's
then
following
it's
a
list, so it stops.
Yeah, so it just stops. It's totally, yeah. And by the way, this is one cool thing is I can actually click on this and, you know, see like my list is 0 here. So this is something new in the latest Elm. It's really cool. Gives me all of my model, and you can see like the different, you know, like walls and ground and things like that there too.
You can also see on the left side there the state history as it gets a sequence of advanced commands every second.
And so I just
it subscribed to.
I just did a set target and it reset the target, so you can see all these events happening. Fun.
Of course, now we have to figure out how to make set target do something that makes it actually move. So
that's right.
You just saw setting the target didn't make it move anymore.
That's right. So we really need to set its path, right? Because we know that it'll follow a path. So all we need to do is set the path.
All we need to do is implement a star in Elm.
So our target path needs to be set to a new path, right? And we need to say new path equals, and then we need to do our pathfind function, and we need to tell it where we currently are. Where's our character.x? Where's our character.y? And then we know where we're trying to go because the target is now x and y. So I'll say x and y. That's our target x, our target. Where did you click?
And then we need to know what our obstacles are, etc., walls and everything else. So we'll need the arena.
So let's pass through our arena as well. Awesome. I'm going to go ahead and just dump all of my functions in here. I have honestly no idea where you're supposed to put them in an Elm program. There's probably a specific, you know, order, but I'm just going to go ahead and do this. So arena. First, we need to know what is not arena. Sorry, Pathfind. What is our you know type declaration?
Right.
So we are taking an int.
Taking in the int of each of the character positions and the target positions and the arena, and we are returning naively, we could return a list of, maybe not even naively, that's what we're trying to get. We need a list of XY tuples, basically. So
that's right.
They move along here.
Yes, exactly. Now, I'm thinking that we should declare a type with that. You know, just call it path. I don't know if that's the best way to go, but
seems reasonable to me. That's a good type alias.
So let's see here. So essentially, we already talked about it. It's a list of tuples. Actually, let's just use records for that. Path equals list x int y int again. That's really simple. That's what did we already have a path?
We do not, but we have something else that has x.
Where did path come from? No, I did that already. Sorry, guys.
Oh, you did. Well, brilliant.
That's funny.
The refactor that we're not going to take time for today is given the number of places where we have XY pairs, it would probably make sense to abstract them into some kind of point and do that, etc. We won't do that here, but you can see why it might be useful to make that abstraction if you were refactoring this.
That's right. So I define, or I bind variables for each of these, except for the last one, which of course we're returning in my new function declaration. And so what we need from here is, of course, our A-star algorithm. I'm just going to return.
Just a simple little thing.
Exactly. I'm just going to return a list so that it continues to compile here. Refresh. Now it's running that code.
And that code is returning an empty list every time.
Every time I get a new path, which is an empty list, which, by the way, if I refresh and let it go, it like moves. But if I refresh and click something, then it resets the target path to just nothing, so then it doesn't move. So we know it's working. All right, cool.
The reason it's still moving is because of that dummy target path we created initially.
Right. So the way that A-star works, I think, is, of course, we need another one of these let-ins. You'll see this a lot in functions. So we need a closed set. These are basically all of the nodes that we have explored. Like we have all these little spiders going out there and like finding the paths and trying to find the most optimal path. We have an open set, these are the ones that are we're currently like actively looking at and saying, hey, which ones on the forefront are the closest maybe to the target. We have and so we need to run those through this algorithm. Now I'm going to create a type here. I'm going to call it actually a type alias. I'm going to call it a path node. And I'm going to say this is x is an int, y is an int. And then we need to know where this particular path came from because we need to be able to trace it all the way back to its origin.
Right. Once you find an optimal path, you need to be able to work back through it.
Right. And then we have a cost, which will be a float for hopefully reasons that'll become obvious. We need to know
triangles.
Yes. So if I just say path node here, like it came from another path node. Yeah. Unfortunately, the way that Elm works, it would just be an infinite recursion, like an infinite type. So we can't do that. We have to create like an intermediate type called, we're going to call this path tree. And the way that regular types work in Elm is they're like enums. Just think of them as enums. So we have an empty.
One thing or another thing or another thing or another thing. But in this case, we just have two options in it.
Yeah. You might have a predecessor, which contains a path node, which is nice because it protects this path node from this alias.
Mm-hmm.
So it won't just continue to just over and over and over recurse forever.
Right. Out of memory errors are actually a problem. So
yes, exactly.
Basically what we actually are doing here is using references, which have a little bit of under the hood knowledge here. Setting things up with references like this keeps you from ending up with a type of infinite size because references to other items are of a known size. So this works nicely.
That's right. So in our pathfind function, we need to actually explore these. So I'm going to say explore nodes. I'm going to pass in the open set and the closed set because we do need that. And we need the arena because we're actually exploring the territory here. So this explore nodes has a particular type. Let me find that. List of path nodes, right? Because that's what we're basically, both of these are lists of these little nodes that we're creating with costs and things like that. Another list of path nodes because that's what closed set is. And we get an arena. And then we will return a list of path nodes. So this will be a list of basically the completed list. Like we're done exploring.
If you're curious about the scenario where you're at the origin, thinking about what these path nodes will be, the reason that our parent type there has, our tree type there, I should say, has empty as an option is wherever you start, you don't have a came from. You came from where you are. And so that's why we defined that tree that way. It's always possible for a tree to have a root node, and you need something like empty for that.
Right, exactly. So explore nodes, this one I'm less confident about, but we're going to forge ahead and see how it works. So we have a let in again. We need to find the current node that we're exploring. So in the open set, which by the way, I have an empty set where that will never actually get explored. We need to actually, we need to start with something. So let me go.
That's in A star, your open set, anytime you're in any given location is the set of nodes immediately around you. So we'll start with the nodes immediately around us and build out from there.
That's right. Now remember I said that it could be empty, and Chris was explaining why it can be empty. And the cost we're going to say is 0, because when you start at your current character location, the cost is 0. You don't have to move anywhere, right? So just so everybody knows, cost is like how long will it take me to get there? How much effort does it take me to get there? Because if you're going through like mountains and stuff, then that could be a problem. In our little thing here, you can see that there are slightly darker sections here. That's because I set the cost to 2 rather than 1. These are more costly to go through. Okay, cool. So we have our open set. Now we need to find which of these, because there could be more than one. Currently there's only one, but we need to find which one has the lowest cost. The reason for that is you don't want to be following a node way off into the boonies somewhere. What if it were Minecraft where you like literally have no edge? You would never find it. You always start with the one that is the lowest cost, because let's say that your target is only a couple blocks away. You want to find that really quickly. You want to just like expand out and boom, find it. So the origin, what we need is a list. Let's sort it by cost, lowest to highest, and then just grab the first one. So list dot sort by dot cost. This is a shorthand in Elm, just says by this property. And we want to do the open set, right? And then if you've ever done Elixir, you'll notice, you'll recognize this. This is a pipe. The difference between Elixir and Elm is that this pipeline, it adds the value to the end, the last argument, rather than the beginning. That's because of automatic currying.
Yep. Anyone familiar with F# will recognize it similarly. Same operator.
List.head is like list.first in other languages. Mm-hmm. And then because what we get back is a maybe, because it could be an empty list, we need to like disambiguate that. We need to say maybe.with default. And then this will never happen, but I have to return the right type, which is kind of annoying. But
whereas I think it's great.
It is nice, but in this case, it would never happen. So actually, I don't know if that's the case. It could happen. There could be a nothing, and in that case,
right. If the list is empty, then you would have.
So maybe I'm doing the wrong thing here, Chris.
Quite possibly. So we're trying to find the origin, and the origin is where we're starting. We already know where we're starting, right?
Right. Is there ever like a situation where explore nodes gets called? We will come back to that, actually. I think that I accounted for this, but we will see. Okay, so Yes. So we have the origin. So now we have the beginning node. We've pulled that off of the list. It's the one with the lowest cost. This is the one we want to explore next. And as some of you may know, this is recursion, right? We're going to be recursing through this. It's already 1:30, Chris. I don't know how fast we're going to be getting through this. So we need to find out what our neighbors are for this node, right? So let's use a node neighbors function. Let's pass in this origin that we just created, and we need to, give it the arena. And I will be coming back to this. So node neighbors
are going to be, as I mentioned before, all of the things around us, but with the constraint that walls aren't valid neighbors. So we'll look at our arena and say, is this thing a wall? If it's a wall, we'll not include it in the list we return. If it's not a wall, we'll return it with, well, it'll be a path node, so it'll have a cost and a position and everything else.
Right. So in order to...
it came from, so that might be the wrong type.
So I guess the fastest way for me to do this is just type it out and then explain what I'm doing. So list.filter map. So this does a map. It returns certain things, but if we return nothing, then it won't be included in the resulting list.
Right.
Nothing
here is part of the maybe type.
Yes.
Just something or nothing.
Okay, and what we're doing here is we are currying a function, which basically means we're giving it some, like we're preloading it with information. It returns back a function that has that preloaded information, and then we can use that function on every element of the list.
We'll define that function in just a minute, and that'll make more sense then.
Exactly. And then we need like this grid. It's like a 3x3 grid around, with the center being our node, because those are the different directions that you can go around. So I'm going to use this list map2 function. This right here is like this built-in thing that will create tuples. Yes. Which if you're not familiar with tuples, they're just a set of like two things attached together.
As long as they're a two-tuple.
Yes. So it'll be like -1, 0, 1, and then we have another -1, 0, 1. So this would be like horizontal and vertical, X and Y.
Missed a couple commas.
I did, didn't I? Okay. Now we need this check node.
Mm-hmm. Which obviously the first two arguments are going to be a node and an arena.
Because we're preloading those.
Right. But what is it that we take next? Well, we're going to take a tuple of ints, that is the X and Y positions.
And that's what this is generating. This is generating a list of those. Yep.
Right. We're generating a list of those tuples. So we're mapping over the result of calling this check node function on each of the items in that list of two tuples.
Yep. So basically just think of it as looking through, sort of like on a keypad, right? Like 1, 2, 3, 4, 5, 6, 7, 8, 9. We're looking at each of those around us, and we're comparing it to the arena, and then we are maybe returning a node, because if it's a wall or outside of bounds or something like that, then we want to return nothing. We don't want to actually look at that. So we're going to say it's a maybe path node. So we have a node, an arena, and an offset, which is like -1, -1 or something.
Yep.
So case offset of, if it's a 0, 0, that means it's our node, it's us. We want to say it is nothing because we're already exploring that, right? Otherwise, if it's an X and a Y coordinate, then we want to, and we'll do another let in here.
Right. Here we have to check, is this a wall?
Right. Actual X, now we only have a -1, -1, right? So we have to look at our node X, and we have to add -1 or whatever. Whoops. No. Actual Y.
Really helpful editor.
Yes. Node.y plus Y. Adam, by the way, is awesome for Elm. Yes. Actual, now we want to find what that terrain is. So I'm going to make a function called arena terrain. We'll give it the arena, we'll give it the actual X, the actual Y, and it should return back like a terrain block.
Right.
So let's before we go too much further, let's create that arena terrain. It takes an arena and an int and an int, and it returns a terrain, maybe a terrain, right? Because if it's out of bounds, it may not have.
Right. If you're at 0, 0, -1, -1 doesn't even exist. So.
Yep. Oops. Yeah.
We would prefer not to explode things, and in fact, handily, Elm won't actually let us do that. If we tried to do that, it would give us a compiler error.
Yep. So we need to. This is a little funky, but lists in Elm, you can't just random access them. So we have to convert this two-dimensional list into a two-dimensional array, because array has this great function called get. We're only using it for here. We could store everything in like an array for all time, but yeah, I'm not going to worry about it.
Right. People who are curious, lists in Elm are linked lists as underlying data structures, and arrays are arrays, and therefore arrays are suitable for random access. Lists are more suitable for moving through the list progressively. So it depends on what you're doing, which one is the appropriate choice. Know your data types.
Yes. And so this basically I'm taking this function, which from list will just create a, and because I have a bunch of lists, I need to just use that function over and over and over. So I just throw that function over to list.map. It maps through all of the different lists, creates a list of arrays, and then converts the outer list to an array. So basically, that does the job. We get the proper row using y. Remember, that's an integer.
Now, array.get gives us a maybe.
And by the way, row would be like y. No, I can't do that because I already have a y up above. So I'll say row and column. And then this is a column, but I don't need, because I'm returning this. In is kind of like your return statement. So because we're getting a maybe, like Chris said, we have this array.get x, but we get a maybe out of that. Now we need to do maybe.and then.
Right.
And to be honest, Chris, I don't understand this. But
so maybe.and then, well, when we did array.get y from the arena array, it gave us a maybe. Basically, that row there we could call maybe row. And when you get a maybe back, and then is a handy thing that says, if there is something in it, then perform this operation on it, which is in this case array.get x. If there's nothing, just do nothing. So you can think of it as sort of being a railway which splits, and if there's already nothing, well, we're not going to try to unwrap what's inside of it because that would explode. That would be your standard JavaScript. Undefined is not an object. Yep. Boom. And then lets you short circuit that, and it only applies array.get x from that row if row exists, if row is just something.
Got it. So it's very much like active support in Rails.try. I don't know if you're familiar with Rails, Chris, but there's a .try, and basically you can try methods on an object until something returns nil, and then it just no ops. So very similar to that.
With the exception that, and this is worth clarifying, unlike nil, it doesn't percolate into the rest of your program invisibly. Maybe always returns clear, like you always know that you're dealing with a maybe, and so you never get the
maybe is one of the most annoying things, but it's annoying on purpose. It's annoying because it tells you, hey, you need to handle the chance that this possibly is the nothing value, and that's a very big deal because you can't have runtime crashes then by calling a function on something that doesn't take a nothing. Okay, so now we get the actual terrain back, and this should be this is a maybe terrain. Mm-hmm. So we need to check and see, is it a maybe or nothing, I should say. If it's nothing, then remember, we're checking this node. We want to return nothing.
Right.
If it's a wall, we want to return nothing.
Return nothing.
Because we're not going to explore walls.
Right.
Otherwise, and just by the way, is like the way of it's in a maybe. It's like this is a real value.
Right.
we're returning a real
It's the
value.
same kind of thing as in the type we defined above, where we had wall or ground. Just is the one that says
so we have
a thing that takes an argument, and you can construct a just type with it.
That's right. So these are the justs we're going to be getting: wall and ground, 1, 2, whatever. So we're just going to bind n to the value. And we need to return, again, we can return a maybe path node. So now we need to return a just path node. And a path node, if you remember, it's a record that consists of an x, which will be our actual x. So you saw that above. We have our y, which is our actual y. We're creating a node on that terrain object, like on that tile. It came from, this is our predecessor, right? And then our predecessor is this node that we are like jumping off of. So like we've got a new node and it came from us.
Yep.
And then we have a cost. So the cost is like, we need to keep adding to the cost. If it's really expensive to get to me, then it's going to be expensive plus n to get to the next one.
Cost is additive.
Yep. So we're going to add that n to my cost. Now, one thing I'm not taking into account right here, which
we might just call that cost.
Right here?
Yeah.
Nice. Oops. Good idea. So my cost. The problem here is if you go diagonally, then we need to, yes, we need to do, now I was talking to my brother-in-law who's a mechanical engineer, and I was saying, for some reason you have to do like 1.4 when you go diagonal. He's like, well, it's the square root of 2, obviously.
Obviously.
Okay. I knew that.
Once upon a time.
So we should probably account for that. And that means we need a let, I guess. And
as an aside about refactoring, so whenever you see a bunch of let-ins, it's often a good target for later refactoring. So
yes,
if we were going to clean this up, we would probably turn this into some functions that handle these things, just passing them values. Your general pattern in a language like Elm or PureScript or F# or any of these is try to turn things into pipes of functions rather than really deeply nested expression bindings like this.
Exactly.
For now, however.
Exactly. Yes, that's a very good point. And you're kind of like going further and further and further to the right. So
it signals you loudly and clearly. You probably shouldn't be doing this.
Yes. So I'm actually going to call this C, and I'm going to say cost equals. And then, so if neither X nor Y are 0, then that means we're going diagonally, correct?
Yep.
So we would need to say C times 1 point, or I guess I could do the square root of 2. I'm just going to say 1.4. Sorry, Daniel, my brother-in-law. Otherwise, we just want C, right? So this is like, it's because if you go diagonally, let me just show you. Like if you go diagonally, like that's further.
You can just do square root, man.
What's is this SQ?
It's SQRT, yeah.
Times SQRT2, is that right? Nice. Okay, so our cost gets multiplied there. Yay, that works. That's because like this is shorter than this, so this needs to cost more. All right.
So now it'll be node.cost plus C.
No, I assigned this.
Oh, you're right. Never mind.
I changed it to C there, but okay. So we have. This is nice because Elm just told me where I left off originally. We have this explore nodes thing here. Help me out, Chris. I'm not sure where I'm supposed to be at.
Okay, so we explore nodes. Why does it think?
Oh, yes. Okay. Sorry.
Yes.
So we
have to bind that returned set of.
Yes. And then what we need to do with all of these nodes that we've explored now, which, by the way, I don't think we did all of the right code, did we?
I don't
think we did that. So we got our neighbors here. Okay, cool. All right, this is actually where we're supposed to be.
Yes.
So we got our neighbors. We need to make sure that we got our neighbors, but they could already exist in what we've already explored. Like we might be running into another path, right?
Right. And if it is, what we want to do is keep whichever is the lower cost. So if the one we just found here is lower cost, then we'll shove it into the open set. And when I say shove it into the open set, that's actually a lie, because Elm uses persistent immutable data structures under the hood. So we'll actually be returning what looks like a copy, but doesn't use the memory and creation costs of doing a full copy, which is
that's a very important point. Yes, because naive immutable languages are very inefficient.
Very. But Elm is not naive, and it uses good data structures. So it's going to give, we're going to give an immutable copy from the perspective of our code of open set back and close set back with the updated things that way.
That's right. So we get our closed set, which is a list of path nodes. We get our neighbor node, which is one node, and we're going to return, potentially a path node, because if my neighbor, if the neighbor that I'm looking at happens to land on a path that was more efficient coming the other direction, then we don't even want to go that direction. We've already explored that in a way that is more efficient. Like if we overwrote that, then we'd be like saying, go way around this thing.
Do more work.
Yes, do more work.
And as you may recall, doing filter map over something that's a maybe will just drop all the nothings. So we're going to look to return a just only if the closed set doesn't already include something that's a lower cost than what we have here.
That's right. So we have our closed set, and we want to filter out, and I'm going to use this kind of lambda syntax. This is like an anonymous function in JavaScript. So \n just simply says bind n to each of these items in closed set. And then what we need to do is look at the n.x and check if it's equal to the neighbor node.x and
n.y, neighbor node y.
Because the way that we tell if they're in the same block is just looking at their x and their y. And then we grab the first one off of that, because if there was a function that just said like list.find, that would be nice, but there isn't. So we have to use filter and then head, which is like it'll pop the first one off.
Right.
There should only be 1 or 0.
Right.
Because of that,
if there are 0, it will be a nothing.
Nothing. And then in that case, it's a new node. Like we're going into unexplored territory, so we want to make sure that our neighbor node is explored. If it's something else, then we now need to compare the cost. Like there's 2 nodes. We need to see which one is on the same space. We need to see which one is lower cost and return that. So we need to return only the neighbor node if it's lower cost.
Right. So if neighbor,
Oops. Then we'll return that. Otherwise, we don't want to do anything, and the reason for that is because we don't want to explore already explored territory.
Right.
With lower cost. We do if it's a high cost, because we can come in there and say, hey, we've got a better path. Let's re-explore this with the better path. If we were really smart, we could like figure out a way to optimize that, but we don't have that much time. We only have like 10 minutes left. All right. Well, I can
warning. We're probably not going to finish the whole thing.
Well, you know what?
We're getting close though.
Yeah, we're doing okay. We're doing okay. Okay, so that's cool. I save and it says cannot find variable. Oh yes. So I need to import array.
Right. We have to actually import modules if we're going to use them.
That's right.
This isn't Ruby, people.
Refresh.
Sorry, I'm a Python guy. I have to troll the Rubyists a little bit here.
That's right.
Explicit is better than implicit. Come on.
I'm a Ruby guy, so I'll refrain.
Mostly I'm trolling him.
All right, so we're doing quite a bit of work here, but nothing's actually changing.
Right.
So
we've done a lot of the underlying work, but if we were to refresh our map thing right now, it would still do the same thing.
It just does the same thing because we're not actually changing the node.
Right.
Or
we're still just returning an empty list.
That's right.
Every time.
So, where am I? What am I doing?
Have found neighbor nodes and
oh yes,
lower cost nodes
right here. So
mapped those. Yep.
Okay, so now we have our neighbors.
These are the neighbors to explore.
That's right. So now what we need to do is create a new open set, which will, and by the way, I can't just call it open set. Like it won't, Elm will not allow me to rebind that, okay?
Right. Confusion ensues.
I'm just gonna type this in. But this is again another lambda, and .x is not equal to origin.x, or and .y is not equal to origin.y, and then open set. Okay, so plus neighbors. So let me try to remember why I had notes to do this. We want to make sure that, we are removing, this right here removes the current node from the open set, and because we are now done exploring it, right? Like we don't need to keep exploring it unless it's reopened by some other node. So, and then we are adding the neighbors to the open set. So the open set basically expands by the neighbors, and we remove the currently explored one. We need to move that though. We need to move the current node that we're in into our closed set. So I'm going to say new closed set equals, and we say our origin closed set. So this is just basically prepending, and prepending is faster and better
because it's a linked list.
Linked lists. That's right. And then this is where earlier I was worried about sometimes returning or calling it on an empty list on line 157 here. But what I'm going to do is check the length of open set. And if it is greater than 0, then I call my same function again, explore nodes. So this is our recursiveness. We send it our new open set and our new closed set and our arena. It needs all that. Otherwise, we're done. We just need to send the new closed set, which has everything we've explored, back. And that's how we get our list of path nodes.
Right. Notably, recursion is, so if we were doing this in something like JavaScript, the way you would naively at least build this would always just be with a loop that would basically push things into an existing array or something like that. And you don't have for loops in Elm. You do have good support for recursion so that it doesn't blow you up with an actually infinite recursion.
That's right.
Although, it's the last expression, so that should be fine.
Yes.
Field recursion optimization is a thing.
It is. And you do have to watch for that. Trace path back. So we need to go, now that we have all of our nodes explored everywhere. And by the way, we're not dying when we find the target here, Chris. We probably should. I'll come back to that though. What we're gonna do is actually just explore the whole map. So that's what we're doing right now. It's very, very naive. You can stop when you find the basically what happens here is this will probably find the most. This is almost certainly going to find the lowest cost path, but it'll be very inefficient. If I stop when I find the origin, I could find a somewhat obvious path to get there, but it may be not the most efficient one. I don't know. The math may or may not work with that, but we'll come back to that. So character X, character Y, we've got that up above because we need to know like where are we going back to. The target X, actually we don't need to know where we're going back to because when we run out of came from properties, when it becomes empty, that's the origin.
Yep, it's origin.
Okay. Target Y, and then all of our explored nodes. Okay. So let's make this one. Trace path back. We'll take an int.
Int and an int. And a list of path nodes.
All right. and it will return a path. Okay, so the first thing we need to do is target X, target Y. We need to actually find the node that found the target.
And you also forgot your explored nodes argument.
Oh.
No, not there. Your.
Oh, right here, right here. Okay, explored nodes. All right. So we need to loop through. We need to do a list.filter of our explored nodes, right? And then find node at target X and target Y. Again, I'm currying here, which means that I'm preloading that function with an X and a Y.
Right.
And the last one will be the path node. And it needs to return a Boolean, I believe. X, Y, node X equals X, and node.Y equals Y. And I don't remember what the order of operations are here, so I'm just going to...
Parentheses never hurt anyone. Lispers.
Yes, lispers. Okay, that's good. And then we need to pass in the explored nodes. Okay, so we get the... oh yeah, it's telling me I'm not returning a path. That is true. So I'm going to use a pipeline. We're finding the proper node. Then we're grabbing the head of that filter, or of that list, filtered list, which should only contain one. It may contain 0, by the way.
Right. So it's a maybe.
So this one needs to be like the target node, right?
Mm-hmm.
This is a maybe. And I forgot my let.
Yep.
I actually think we're not too... I know it's only 2 minutes left here, guys, but I think we're very close. And we will put this up for watching later. If you got to...
People have to drop out. Don't worry.
So we've found our target node. This is great. Now what we need to do is we need to... We should have references to all of these, right, Chris?
We should. I'm not sure we have collected them anywhere in our current setup. Our traceback path should take target X, target Y, and the explored nodes. Where
our came from.
We need to use the came from as we're going through this traceback path.
That's right. So what is the function to do that? I mean, I have this target node. Well, I know one thing. Case target node of, and if it's nothing, correct, then we need to return an empty path, because basically we can't get there, right?
Right. So if there's
no target.
Right.
Yeah.
So I think what we need to do here is say target node equal explored nodes, filtering find node. I think that where we're doing the let bindings.
Mm-hmm. What I'm thinking, and tell me if I'm wrong here, we need to basically get the came from node, right?
Mm-hmm.
Next node equals, we just need a recursive function here.
Right.
So,
but we need to build up a list with that. This is a sort of standard case for folding.
Yes.
Of explored nodes, and we're going to fold over that fold that list into...
Actually, I think I disagree. Let me go through this, Chris, and then you tell me if there's a better way with fold.
Sure.
So what I'm thinking is we call a function. Let's see here. So this is the original node. So what I really should be doing, in my opinion, is doing this here. And then doing this case target node of no.
So what you're saying is if the target, right. So now if the target node is in the list, we'll go ahead and pop off the path back. Otherwise,
Recursively node, explored nodes. Okay. I think that I can get there from here, but this is a little bit. So let me think here. So we have this trace path back. I think what we could do is recursively call this. So we're saying we have our current node. What we need to do is trace path back node. Whoops. Okay. Actually, what we can do is case node dot came from of, and then we have an empty, which will return explored. No. We need to pass forward the current. Yes, we do. Okay, so the current list of, or the current path. Okay, and we're gonna construct this path. So we have a path, and we will return a path. So we get our current path, and if we are now at the empty, we just return current path.
Right, we return current path. Otherwise, we return.
We don't need a let here. Otherwise, we if we get another node, a path node,
right. A predecessor, yeah.
Then we need to oops. We need to trace path back.
And predecessor should be capitalized there. And you need to bind. Yep.
Came from. So this is, so we're passing through the came from. We're passing explored nodes unchanged.
Right. Although using came from there is probably slightly confusing since it's also the name of a property on the node.
Yeah, you're right. So I'll just say pred. Okay. Predecessor, and then explored nodes, and now this needs to include
because the predecessor. Oh yes, it does. Sorry, I confused myself.
No problem.
Never mind.
So we need to add to the current path,
right?
Or prepend. Actually, don't know what
cons.
Is that right? Is that right? Yeah, because when we get all the way to the end, yeah, cons. Thank you. Then that will be the first one.
Yep.
Right. Okay. Good. This will not compile, as you said. Path node, but it's a maybe path node.
At line 153.
Or do I need to say like?
So what we're getting back, because target node is, so you can do the case statement of above in the in at 152. The issue we're dealing with here is that target node might be maybe. So you can
yes.
write a case here.
And in this case, there might be a nothing, and there might be a just
node, for lack of a better word.
Node. Right? Or is it lowercase? No,
it would be a lowercase here. Yeah.
Yes, path node, and so we've got this.
Right, and that'll go where target node currently goes online.
I see. Okay. Yes.
And nothing will return an empty path, I suppose.
Okay. That makes sense.
Better to return a maybe path from Pathfind.
Oh, good point. Although actually, I'm okay with it being an empty path, just because we're currently handling empty.
Right.
Fine. So, but you're technically correct. This is a list path node, and we think we're returning a path. I thought that paths were list path nodes. No, they're not. a very good point. When we return this back, we need to actually strip all of the extra information out of it. It just needs to be the X and the Y.
Just need the X and the Y.
Right. So in this case, we need to...
We can list.map that into, or not list.map.
I think so. I think you're right.
Well, path node isn't a...
It's X, so it'd be X equals n dot X, Y equals Y dot, or n dot Y.
Right.
It's a list path node.
Okay, hang on. So traceback path is taking a path node, returning path. I'm just trying to trace through which thing we need to drop where.
So this thing thinks that the...
So instead of pred current path, you need to pass...
I need to do the whole... Okay, this actually makes sense. So X equals pred.x, Y equals pred.y, and then that actually makes it easier because I don't have to do this anymore.
Right.
We're just building it the right way to start with. Hey, it just compiled.
Yay. Wonder what it does now.
No idea.
Because I think we're still returning an empty list up above.
Oh, okay. Gotcha. So where are we using this? We are returning pathfind.
Right.
A new path does get set. Okay, let's watch and see what it does. This is the sort of bug that you will get in Elm. Okay, so I click and I get set target. Oh, am I doing anything on set target? Yes, I am. I'm creating a new path.
So now we have to see what is being returned in Pathfind.
Right. We're so close. We are so close. Target node is not actually used. No, we are. We are using it right there.
But we're otherwise not using it. And it seems like that's kind of a weird thing.
Case
we're only using
target
it
node. Okay.
What is path node? Oh, I see. Yeah, case target node of just path node is right. So trace back the path node. If it has a predecessor, are we setting all the predecessors correctly?
Predecessor is set right here. We are setting it to node, which is the current node. Okay.
Right.
Let's do some logging. Let's see what comes back from Pathfind.
Yes, indeed. Logging is still a valuable tool for debugging.
Yes, it is. So I don't remember how you
given a list, you can do something like list.
Isn't there a debug dot?
Yes, it should not be used in production code. You can import debug and then do log.
Oh, okay. We are deploying this directly to production, so we need to make sure that we're doing. Okay. Oh yes, I need to say this is a new path. Okay, it did. Okay, let's refresh here. And when I click, we get new path, nothing, new path, nothing, new path, nothing, new path, nothing.
Right.
So we have a bug in new path, or pathfind. So the target node, filtering find node X and Y, and we are getting all the explored nodes. We're checking to see if it's there. Wait. Oh, this doesn't look right.
That's what was hanging me up earlier, but I couldn't. I
Is
didn't
this-
have time to figure
Is this
out.
like a I'm missing here. Oh, it doesn't like that.
Correct.
Do I have to say not?
175.
Okay. Okay, still not getting anything, so I was just guessing at that point.
So taking a step back, we are trying to say explored nodes, tracing back through the path from the target node if we got to it.
Right. Find node, target node.
Let's
okay.
make sure we get what we get as target node. So if we can debug.log that, that would be nice.
Okay. Target node, nothing.
Right. So list.path.
Hey, when I clicked on it, then I got something.
Ah, are we finding the node the wrong way?
Yeah, something is blocking us from getting there.
Let's look at what Pathfind is, or what we're calling Pathfind. It could be as simple as giving it the arguments in the wrong order or something.
Yeah, I think so too. So where we're calling Pathfind, we are saying the character X,
and X and Y as the targets.
Nope.
So
yeah, so we're getting that. Our open set gets, let's just debug this. Okay. Open set is X is 2 and Y is 2.
Which is where it is, 2 and 2.
Okay, so
Also 0.
That's correct.
Right.
All right, and then our
explored nodes seems likely to be where the problem is, since that's the meat of the actual.
That's right. So somewhere along, let's look at neighbors. So neighbors, we got an X1, Y1 came from the predecessor. Okay. We got a cost, which is, that looks right. We got an X3, Y3, which is basically where the disk is right now. And we got an X2, Y2. Wait, that is weird. Oh, no, 3, 3 is right here.
Right.
So we got a 1, 1. We got a 3, 3.
But only those two.
But only those two. That's interesting. I think it's our neighbors function.
Seems so, which is interesting because I wouldn't have thought that was the complicated one.
Let's find that. Where did I put
our
that?
node neighbors, I think, would get us there. No symbols found. Lame. You'll have to Command F it. I was hoping that there would be symbols found, but
okay, there it is. Okay, our filter map. We are looping through this thing, so I'm going to let in, let's say grid equals this, debug log grid and grid. Great. Refresh and let's. Our grid was -1, -1. That's it. That's the problem.
Yep.
How do we fix this?
We basically need not just.
You know what I'm going to do?
We need a cross product, but you could just write that.
Wait. I need. Oh yeah, is it a list? It's a list. Just a single list. So -1, -1, and let's. It's all the way down. Turtles, all the way down.
All the way.
0. 1, and then we will say 0. 1. No, sorry, it's -1.
Yeah.
We'll skip 0, 0. So we'll say 0, 1.
Right.
And then we say 1, 0, or 1, -1,
Right.
1, 0, and 1, 1.
There's presumably a function that would do what we needed there, but we don't know what it is, so.
Oh, hey. Uh-oh. Is it working?
It's working.
It's working. Oh, it didn't go all the way.
Got almost there.
We're missing one thing. So this would be when we are creating, or when we're tracing the path back, we need to not start with nothing. What we need to do is start with
the target node.
The
X and Y of the target
node.
Yeah.
Yes, we need to start with that. So X equals and Y equals.
Only an extra 15 minutes, but it seems to be.
I'm actually pretty impressed with with us.
We prepped though.
Yay! Okay. Oh, look at this. It's going around.
So it's going around the higher cost areas. Look at that.
Yes, it is.
Look at that.
Look at that. That is so awesome.
All recursive too.
Okay, so I'm going to move it back here, and I'm going to move it up to this corner here. And then I'm just going to say, go straight across. And in this case, it decides
the cost of going that way is
lower. Was still better. I'm so impressed. That is so awesome.
Awesome.
Well, this concludes our demo.
And look at it go around that so elegantly.
So cool.
Now, the fun thing is we could bump up costs in different spots or change these things, and you could see how it would react to that. But I think you get the point. It's going around the higher cost things.
So for our audience, your homework is to clone down my repo, fork it, and I'll put this on master in a little bit. Your only assignment is to make a different map and then play around with it. Make a bigger map, make a smaller map, and then if you want to, check the efficiency of this. Maybe put 1,000 or something. Do some sort of automatic generation thing. That'd be super cool. Do a pull request back. Chris and I will look at it, and maybe in the future, Chris and I will do another live coding session.
Indeed.
Thank you so much for sticking with us.
Yes.
It's been super fun. Thanks, Chris. Appreciate your help on this.
Yeah, it was fun watching you mostly just smash it. So,
Well, we did some prep, obviously, but it was still really, it was still really fun. I want to try this one, see what it does. Oh, there goes Chris.
To it.
You dropped out of Zoom, I guess, but
it's true.
All right.
Zoom just said Zoom said you've been coding live long enough.
Exactly. Well, thanks a lot, everybody,
for watching. And if you have questions, you can tweet them at us. I'm at Chris Krycho. Jamon is at Jamon Holmgren. We both have super easy to spell last names, and Jamon has a super easy to spell first name to go with it.
Yeah, that's right. It's just like Jason, but with an M. So just think of it that way. All right. Thanks a lot, guys.
Have a wonderful night and Happy New Year.
Bye.